Welcome to Lecture 13 in New N 302. If you remember last time, we talked about a general decay process that also accommodated these generic terms for production and loss. That's what's shown here in this schematic here, this general decay balance. Today we're going to talk about a specific example or specific application where we can start putting some meat to the skeleton, so to speak, of the production term. So we are going to talk specifically about a neutron field. So if we put a sample in a reactor where there's some neutron flux present, and those isotopes that are in the sample, or the isotope that's in the sample, is going to have some cross section, some likelihood of absorbing a neutron, thereby becoming a new isotope with a neutron count of one larger than it had before. And so that's a source, that's a specific example, a very common example that we're going to encounter for this production term. The new isotope that has an extra neutron is getting some production of that isotope just from the fact that this other isotope, it's not a parent in the sense that it's a decay parent, but it's a parent in the sense that because it absorbs a neutron, and that becomes the source of the next isotope. And so we'll talk about that example. We'll develop some expressions to help model the dynamics of that, and then we will determine what happens after the sample is removed from the reactor. So look at the sample in the reactor where the neutron field is present, and then we take it out. What is the time history of the decay there? In many cases, that's a much simpler problem than the activity problem. And then finally, we'll talk very briefly about the application of decay, these foundational principles of decay, and how we can use that in radiodating and determine the age of certain things. But if we look at this general decay balance here, we're going to consider two scenarios here. One where we've encountered this up until now, really, this first column, this X, we have some parent, and it's going to decay into a daughter. There's our parent, there's the daughter, and then we have some light decay products. Could be an alpha particle, could be a beta, etc. And so we're going to now consider this specific example where we have this isotope and it absorbs a neutron and then emits a gamma ray. And so what are the loss terms for X1 in this first one? Well, it's just going to be the decay, and we've already talked about this. The rate of that is just going to be the decay constant, lambda, the product of that, and the number of nucleons, or the number of atoms that the population of those atoms of isotope number one. And the production term for our daughter product is going to be that same thing, just a positive sign this time. So we've again encountered this before. Every time we have a decay, everything the parent loses is gained by the daughter. Now, as we look at the second column here in a neutron field, we ask ourselves, okay, what is an expression that helps us understand how often, and that's what the decay constant does. It tells us statistically how many of these nuclei are we going to lose from the parent to the daughter population. And if you recall back from our discussion of cross-section, that's exactly what a cross-section does. And so we have isotope number one, and so it's going to be dependent on the number of nuclei of that isotope one. It's going to depend on the neutron flux, so the neutron field. This will be in units of neutrons per centimeter squared per second, for instance. And then we're gonna lose these based on the cross section, and so we'll put gamma for the absorption cross section of isotope one. We can look this up if we know the speed of the the neutrons, for example, we can look up that cross-section value, and this will be negative because from isotope 1 we're losing these. As soon as one of those absorbs a neutron, it's lost from population isotope 1, and then it becomes part of the population, part of the inventory of isotope number 2. And so it's a similar principle that whatever in the left column we're talking about just about decay. Anything we lose from the parent becomes a source term for the daughter. It's a similar principle over here. Now x1 and x2 in these two scenarios are not the same, and so it's not a parent-daughter in traditional sense that we've been talking about in decays, but the analogy is exactly the same. Everything that we lose from the inventory of isotope 1, and that's quantified here, everything we lose from that has to be gained by the inventory for isotope number 2. Isotope number 2 in this case is here. And so this is just the same thing, only it's positive. And so if you notice that in front of the N1 here we've got lambda, and in front of the N1 here we've got sigma times the neutron flux. And so mathematically this is exactly analogous to the decay constant. The product of the cross-section and the neutron flux is exactly analogous mathematically to the decay constant. And so what's going to happen then is we might have, during this whole analysis, we might have an isotope that has the tendency to absorb a neutron, so we have to account for it with the equations that we just wrote on the right-hand side here. But it might be unstable, and so we might lose some of those through the decay process. And so we would simultaneously have to account for both of these. And since both are dependent on N1, then it's just a simple addition of the two different sources or the two different sinks. And so we'll get into a few examples of that, but if we look at this in a little more detail, if we say for the decay, so for the decay process, we had this expression equals minus lambda 1 N1 of t. And this resulted in the following. Once we solved that differential equation, we needed to know the initial inventory of isotope 1, but that would just exponentially decay according to the expression shown here, this exponential of minus lambda 1 times t. And so we go to the second column over here, this other application for the absorption of neutrons, then dn1 dt, and instead of negative lambda 1, it's just negative cross-section, the absorption cross-section of isotope 1 times that neutron flux multiplied by n1 of t. And so the equation is going to look, again, mathematically analogous to this, where this now is the exponential of negative cross-section times actually we needed to assume that this is a constant in order for this to work mathematically. And so we'll remove this, and we'll just call this phi naught. And that should just be t there. And so it's an exponential decay, just like the previous one was for the decay. And so with that, hopefully with that understanding now in our foundation, we can do a couple of examples. And we're going to do one by hand. We'll do one by hand and go to MATLAB for a bit. But because at the end of the day, we've got some decay equations that look exactly the same as everything we've been considering so far. And so we can dump that into a system of differential equation solver like we did before. So in this first example, we've got deuterium. We're going to subject this to a constant neutron flux. We've got a value for that. This is going to result in tritium once that it absorbs a neutron, which is unstable, and then undergoes a beta minus decay to become helium-3, and helium-3 is going to be stable as well. And so here's the equations below. I've got a neutron, and I've got deuterium, and on the product side I've got tritium, and it's going to emit a gamma, but then that tritium is going to go through a beta minus decay to become helium-3, and then of course the beta minus and the antineutrino as part of that beta minus decay. But that helium-3 is going to be a stable. So what we're going to do, a stable isotope. So this one will be isotope number 1, this will be isotope number 2, and this will be isotope number 3. And isotope number 1 and 3 are stable isotopes. So we know that the activity of those two and helium-3 are stable. So what that means is the activity of isotope 1 equals the activity of isotope 3 equals 0. I don't have any decays. It doesn't mean that isotope 1 isn't changing to isotope 2, it just means it isn't decaying to isotope 2. Okay, so for part A, we want to determine a set of differential equations that can be used to model the inventories and activities. And so this is hopefully becoming almost second nature to you. You're going to set up d1 dt, dn1 dt, and then you're going to look at, okay, what do I have as sources? Those are positive terms. And what do I have as sinks? Those are negative terms. And so for isotope 1, all I have is a sink. There's nothing producing deuterium here. It's just a sink to tritium. And the sink term is going to be that gamma cross-section multiplied by the neutron flux multiplied by the population that I have of that first isotope. And that is my first differential equation. My second one is going to be in terms of N2. And in this case, I'm going to have a source, and the source is coming directly from my isotope 1 population. So anytime I gain a neutron from in isotope 1, then I'm losing that nucleus, I'm losing that atom, and it becomes tritium. And so that becomes a source. It's a positive value this time. But whatever I lost from isotope 1, I gain in isotope 2. And isotope 2 is unstable, and so it's going to have a decay constant. So I'm going to lose that one. So minus. And then it could also have, in theory, it could also have a cross-section itself. And so we haven't talked about isotope number 4 or 3b or whatever you want to call it, but because this is not going to be helium-3. If I absorb a neutron in the tritium world, then that does not become helium-3. But it is a sink in my expression. I could have, because I'm in a neutron field, I could have a cross-section, a non-zero cross-section, a non-zero likelihood of this unstable isotope, instead of decaying, absorbing a neutron and becoming a different isotope altogether. And so we'll leave it at that for isotope number 2 expression. And then finally, we have our third. And I asked myself, well, what are the sources here? Well, that came from a decay of isotope number 2, and so this will be a positive lambda 2 and 2 of T. That's my source, and then my sink. In theory, I could also have, we've already said that it's stable, so I'm not going to have a lambda 3, but I could have some absorption cross-section here as well. And so I've got an N1, I've got an N2, and then I've got an N3 here. And so I just need to, and then here's my N3, there's my N1, and then here's my N2. And so I just need to set up these differential equations, and I can do this analytically. We'll go ahead and write the expressions analytically. We're not going to go through all the math analytically, but we're going to compare, we're going to use these analytical expressions to prove to ourselves that the numerical solution that we're going to set up is actually solving it like we think it is. So we're going to use this as a validation, so to speak, of our code. But this, what you're looking at here, these are the activation, called the activation, and these are in differential form, and so this will be the activation differential equations. In just a minute we will write out the solved closed form analytical solutions to all these, and then we'll simplify them in the next example. But this is really where we want to start with our numerical solving of these differential equations. And again, we'll compare that to the following. Here's the full solution. So N1 is just going to be minus, or N1 naught. This was an easy one to do by hand. If we know the initial population, exponential of minus my cross section of that isotope 1 multiplied by that constant neutron flux multiplied by T. So that is my expression for my inventory for isotope 1. For inventory for isotope number 2, then if I plug that in to my expression up here for N1 and I solve that out, then I'll find out that N2 is going to be the following. N1 naught times sigma, that's for 1, and then I've got, and that's one thing to remember, is you're never going to see a sigma without a phi next to it. And the reason why is because that, if I multiply those two together, I get the units of 1/2, which is the unit of the decay constant. And so I can just add those together. This will be lambda 2 plus naught times my cross section 2 minus 1. And all these are absorption cross sections. And we multiply that by the exponential of, there's the exponential decay due to the absorption in isotope number 1, and this is competing with the exponential decay of a combined effect of decay, so my decay constant, and the absorption of isotope number 2. So that's my expression for N2, and then N3 gets a little more messy. But don't worry, we will be simplifying these again in example number 2 in just a minute. 1 times phi naught divided by the same denominator here. Multiplied by the exponential of 3 phi naught T minus the exponential of minus 1 phi naught T divided by sigma 1 minus sigma 3 times that phi naught, and then we have a final term down here minus the exponential. My numerator here is going to be and divide that one by lambda 2 plus the difference in the cross sections there, multiplied by that neutron flux. And again, you can do this by solving these differential equations analytically, but I think it's probably important to note here that these assume, just like we've done in the past, n2 naught equals n3 naught equals 0. We just have, in the beginning of time equals 0, we have nothing but that first isotope. So I can solve these, I can plot these, but part A was just determine those differential equations. Part B, I want to determine and plot the tritium activity, so that's isotope number 2. I want to plot the activity. I have an expression for the inventory. In order to get activity, I just multiply that by my lambda 2. And so I want to look at that over a 40-year time frame. I want to repeat that for a 300-year time frame. So if I come and look at the solution here with the MATLAB script, I'll walk you through this a little bit. This is just a general script. We'll go to this activation script here in a minute, but I want to be able to say, well, maybe we'll start with this one. I want to be able to say, tell me what your isotope number 1 is. Tell me the number of, tell me Z and A. So tell me the number of neutrons or protons, and tell me the number of nucleons. That's Z and A. And then I can go look up all the cross-section data. I can go look up whatever I need to about that isotope. I also need to know the phi. I need to know that neutron flux. And I want to be able to just model, if we go back to the expressions here, I want to be able to model these here. And if I can model all those numerically, then I've accomplished what I need to. So this is the same as what we did before in the last lecture with a set of differential equations. In this case, I want to populate those. I'm basically just creating the differential equations that we saw just a minute ago. We'll come back to this one, but in this example, so I am first saying that my initial isotope number 1, has 1 proton and 2 nucleons. So that's my deuterium. That's isotope number 1. Avogadro's number. It's not given a mass in the problem statement, so I'm just going to assume 1 for 1 gram. So I can get my initial inventory of that isotope number 1. And then these are my initial values for isotope 1, 2, and 3. Again, following a similar pattern as we did in the example from lecture 12. And then the neutron flux that's given in the problem statement was 10 to the 12th. And now I want to call the solver. So initially I'm looking at doing this for a 40-year time frame. So I've got my final here is going to be 40 years times 365.25 days times 24 hours times 60 minutes times 60 seconds. So I'm going to get this in units of seconds, and I want to start at 0 and go to that value. That's my time window that I'm looking to do this numerical simulation across. And I just call the function ODE45, which is a solver for a set of differential equations. I just need to build them. I need to tell it where to look, and where to look is this function N activation, and for neutron activation. These are the activation equations. And N is the number of isotopes in each of the 3 isotopes that I'm trying to model. And so that's one of the things that I am varying. I want to vary T. I'm not varying N, but I'm varying T, and I want to see the response to N. That's what this section here means. And this is what I call that function. We'll go back to that one in just a minute. And I also need to input for this solver here, this numerical solver, I need to input the time window and the initial conditions, which I've already specified. And the output to that one is going to be these vectors, 2 vectors, one of time and one of N. This N is going to be actually a matrix that's 3 columns wide, one for N1, N2, and N3. Again, in principle, there's nothing different here than what we did in the last lecture with the pure decay problem that we were up against. And so going back to this function here, I want to look at at isotope number 1. And I want to say, what's the production, what's the loss? Well, the production was 0. If that isotope 1, the only changes were due to the neutron absorption. And so I go and I use this function that gives me my absorption cross-section. The inputs to that are my number of protons and the number of nucleons. I'm going to convert this from Barnes to value of centimeters squared. And so this is now the term, phi multiplied by sigma is what I'm calling the neutron, the loss term, Ng, neutron Ng, so it's the gamma cross-section. So that's the loss term. That's the only loss term I have for isotope number 1. Isotope number 2, notice my proton count did not change. I just absorbed a neutron, and so my nucleon count increased by 1. My production term, that P2, is going to be what the loss term was over here. My loss term is Ng1. Well, my production term here is Ng1. And I look at 2 different loss terms here. So I have Ng2, similar way that I found Ng1. I've got phi. I'm looking up my cross-section now. I've got a different number of nucleons, and so I got to look that up. Again, convert it from Barnes to centimeters squared. And then I need to do the component of the loss that's due to the decay. So I need to find the decay constant. And so I've got this function half-life, which again, the only inputs there are Z and A. And that's going to give me my half-life. That's going to give me my new number of protons and my new number of neutrons. Because in this half-life, I'm using this table, which now is posted on Canvas. What this is a table full of columns, and the first column is your number of protons, just like it was for the AMU table. The second column is the number of nucleons, and the third column is the half-life in units of seconds. And so a lot of these half-life data sometimes are represented in minutes, sometimes hours, sometimes days, sometimes years. These have all been converted to be consistent, so they're all units of seconds. But it's the half-life. This is not the decay constant, this is the half-life. And the rest of the columns represent the decay path. And so this is the percent likelihood of any decay path. So the first one's going to be the beta minus decay path, then it's going to be the alpha decay, then beta plus, then electron capture, and then spontaneous fission, which you're not going to see any non-zero numbers there till you get to a very heavy nuclide. So I can use these numbers here to not only read off the half-life, but I can look at the rest of this data and I can see what type of decay I have, and therefore I can tell it in that function. I can output the new number of neutrons and the new number of protons, depending on which decay path I ended up taking. So you've got that available to you. You can build you a function just like I have that as inputs is just the protons and nucleons of the isotope, and then the outputs of that can be the half-life, and then you can output the decay path, but in my function I just go ahead and say, okay, that's the decay path. If it's a beta decay, here's what's happening. If it's an alpha decay, here's what's happening. I'm going to lose 2 neutrons and 2 protons, and so on and so forth, depending on the decay path. But once I have that half-life, then I just say the log of 2 divided by that natural log of 2 divided by that half-life, and that is my lambda 2. And so if I go back to my handwritten notes here, I've got these 2 terms, which both are going to be loss terms, and multiplied by N2, I've got this. I've got my cross-section and my neutron flux, and then I've got this here, which is just my decay constant. And so to account for both losses together, I'm just going to add those together. So going back to MATLAB, then I'm just going to add those 2 together. That's my loss term. And all the positive and negatives I'm going to take care of in just a minute. But then I go to isotope 3. isotope 3. The production of 3 is just going to be lambda, and I could also have I got to account for the losses here. So my production is lambda, any decay from isotope 2 becoming isotope 3, that's what I'm gaining. And then my losses, again, in a similar fashion, I'm going to just add together that neutron absorption loss path and the decay path. And once I do that, then it is quite literally just finding or quantifying those terms in terms of losses and production. And so this dn1 dt, that was just the loss term for 1 times n1. And then I had production of 2, which was really the loss of 1, times n1, minus the loss of 2 n2. And recall that this loss term here had two quantities, 2 paths in there, one from absorption, one from decay. And then my third isotope, I'm calling my third isotope the helium-3, and I've got the production term there times N2 minus the loss times N3, L3 times N3. And so this function now is built to be solved here. And again, the output of this is just solving those differential equations. Time vector, and then a matrix that has just as many rows as the time vector does, but then in our case we'll have 3 columns. And so these equations are quite standard when you talk about the activation problem or activation equations. That's what we're talking about. Bring in a stable isotope, it's going to absorb a neutron, typically going to be something that's unstable, so then it can decay, but it also could absorb a neutron again. And then that decay, that daughter product, is either stable or not, and could also absorb a neutron and become something else. So, and then once we have these, then I can just calculate my activities. Here I get my cross sections. Here I get my half-lives, and lambda 1. Well, in this case, I'm lambda, not lambda, but my activation 1 and 3, in this case, since they're both stable, are going to be 0. But lambda 2, or my activity number 2, is just going to be, my activity in general is going to be n times lambda of that. N1 times lambda 1, N2 times lambda 2, and N3 times lambda 3. And so that's all this is doing. In this case, I'm forcing the lambdas from 1 and 3 to be infinity, which means I don't have any decay. Okay, and then I plot the results. In this case, I want to convert my seconds back to years. That's what it asked, that the problem is specifying to plot this in terms of 40 years, and so it makes sense to do years, label my axes properly. And then I take the activity and I divide that by 3.7 e to the 10th to convert from becquerel, which is decays per second, to activity in units of Curie. And then I do the same thing in figure 2, except I'm plotting the inventory of each of these in relation to what the inventory I had in the beginning. Okay, and then here's the analytical solutions. So you can walk through these, and you can see that these are exactly the same as what we had on paper just a minute ago. And I will say that doing it this way, you're bound to make some mistakes with parentheses, so be careful there. And so I'm calling this n alternate, and it's also going to be a 3-column vector. And then I find the activity alternate of each of those, and then for these I'm going to plot those in figures 3 and 4. And so activity alternate using the analytical solution in figure 3, activity using my numerical solving of those differential equations, figure 1. So I want to compare 1 and 3, and then I want to compare 2, which is the numerical solving of those differential equations for the inventories, and then this one is going to be the analytical version of that same quantity. So I can just run this, And there's my figure 1 and 3. So that's the activity of 2. You see I've gone to 40 years. And I start at 0, and it looks like I'm ramping up to something. We'll do, I think it was 400 or 300 years, we'll do that next. The main takeaway here is my analytical solution is very well captured by the numerical solving of those differential equations. And as we look at the inventories, it's kind of hard to see anything that's going on here, but what's happening is isotope number 1, I'm hardly losing anything. And so if I zoomed in, you'd be able to see that yes, it's decreasing, but it's such a small value that it's decreasing by. And so in order to see this a little bit better, I'm just going to delete this line. And I'll do the same thing over here. So I'm not going to zoom into that, but just trust me that you can see the... Oh, I forgot I needed to go back here and I needed to get rid of this opportunity for isotope 3 to decay. We only want it to absorb a neutron, because if we look at the expressions that we developed here for N3, we only have the source from N2, the decay source, and then we have the only sink we have is the absorption of isotope 3 for neutrons. And so if I come back here and now get rid of this term, so I comment that out, save that, and then rerun this. And the activation looks consistent still, but it's this one then that if I get rid of this top line, I should see both the inventory for isotope 2 and 3. So what was happening there is, the way I had defined it is, since lambda 3 was infinity, it was just throwing that one out. It wasn't even plotting it. But now that if I want to do a more generic modeling of this, then if that isotope 3 was not a stable one, for instance, if it had a half-life that was something that's quantifiable. And so I can see that I'm capturing both in the analytical sense and the numerical sense. I'm capturing the physics that I'm trying to set out to capture. So let's redo this for call it for 300 years. And so we're just going to come up here, and instead of 40 years, we'll do 300 years. And this might take a few more seconds to run, but it shouldn't be too much longer. It's going to be much, much longer if I try to do a million years or something like that. But okay, there's my solutions. And what is worth noting here is that the activities now, again, analytical and numerical is the same, but the activity seems to be flatlining to some value. And what you would find if you went even further than 300 years is that eventually this activity starts to decay back down. It's a very, very flat region for a very, very long time. And so for the time window that we would actually run this experiment, we're not going to run an experiment for 300 years, not even 40 years. And so for the intents and purposes of modeling the activation dynamics, we're going to go and simplify these expressions here in just a minute. But it looks, from this plot, looks like it's just flatlining. It's reaching some asymptotic value, some saturation value. And the equations are going to reflect that here in just a minute. Okay, so let's go to example number 2. In example number 2, we're going to take these full expressions, the one that I just wrote by hand. They're here for your perusal. But we want to simplify these. We want to take those full expressions and we want to develop simplified expressions making use of the fact, there's two things here we're going to make use of. The first is that this value, lambda 2, since these have the same units now, sigma times phi is going to have units of 1 over second. So I'm going to compare that to lambda. Lambda 2 is going to be much, much larger than the product of my cross-section and the neutron flux. And that's going to be true for isotope 1, 2, and 3. Because lambda 2 is in this scenario, lambda 1, lambda 3 weren't worth mentioning because they were stable. 1 and 3 were stable isotopes. It's only lambda 2 that we care about in terms of decay. And so we're going to assume that this is much, much larger. And we'll validate this at the end. And then we want to take this expression here, the product of time, the time that's of interest to us. So, for instance, we're not going to run an experiment for 100 years. If we take the product of that and multiply that by the cross section and the neutron flux, that's going to be much, much smaller than 1. So what does that mean? Let's take this first one. This first expression for the population, for the inventory of isotope 1, for T being much less than 1 over that product of cross-section and neutron flux. If I assume that, then I basically have the exponential of a negative, really small number. And so this then means that N1 of T is going to approximately be N10. It's going to be my initial inventory of isotope 1. It's not really going to change that much. And if we go back to MATLAB, we can delete those other lines and we can zoom in on it. Let's do that really quick. So if we look at the same plots we were looking at before, we'll get rid of the activity plots and we'll look just at the inventory plots. So here's one of the inventory plots. So let's get rid of these two in this case. So you can see that yes, it is decreasing, but over a 300-year time frame, then the percent change of the number of atoms that was isotope number 1 is insanely small, a fraction of a fraction of a fraction of a percent. And so we can quite comfortably make this assumption here. And for N2 then, let's look at this expression in more detail. For N2, then we're going to look at the denominator here. And we're going to say that this is going to be approximately equal to lambda 2 because of this assumption here. So this will be approximately lambda 2. This here, well, the entire term, the exponential of that really small number, this is going to be approximately equal to 1. And then this term in the parentheses here, this will also be approximately lambda 2. I take cross-section multiplied by neutron flux, and I'm not really changing lambda 2. Lambda 2 is much, much larger than that. And so what happens here is that N2 can be simplified to just be equal to N1 naught times sigma 1 phi naught divided by lambda 2 multiplied by 1 minus exponential of minus lambda 2t. All right, so there's my first expression, simplified expression. Here's my second one. And the third one's going to take a little bit more, but we can sort through this. This here, just like before, this is going to be equal approximately to lambda 2. This one here, just like we did up there, this will be approximately equal to 1, while this one here inside multiplied by t, this is going to approximately be equal to lambda 2. And likewise here in the denominator is approximately equal to lambda 2. So then what to do with this middle term? And the answer to that is because we don't have lambdas in there. Whenever we have a lambda or things that we're subtracting or adding together that has the exponential of something without lambda, something with lambda, then we can start making these assumptions just like we've done so far. But in this term here, we don't really have any, well, we don't have any, there's no lambda in there at all. So the way we're going to approach this is look at the Taylor series. And the Taylor series of e to the x is just going to be 1 plus x. And we're just going to take those first two terms. So this first term in the numerator here, this exponential of minus sigma gamma 3t, this is going to approximately be equal to 1 plus x, where x is the argument inside the exponential function, and in this case it's a negative number, so it's going to be negative sigma 3 phi naught t. So that is my Taylor series expansion of that first term. And then likewise for the next term, I'll do the same thing. This will be gamma 1 phi naught t. This is approximately equal to 1 minus sigma 1 phi naught t. And so I look at that now, this numerator then becomes, or this numerator, this fraction, this term we didn't know what to do with, becomes, in the numerator I've got 1 minus sigma 3 phi naught t minus, and then I do the Taylor series expansion of that second exponential. That's going to be 1 minus sigma 1, or gamma 1 phi naught t divided by my denominator here. We can see that this 1, got a minus and plus, this 1 cancels out with that 1, and what I'm left with is, I'm left with sigma gamma 3 minus sigma gamma 1 times phi naught times t divided by sigma gamma 1 minus sigma gamma 3 times phi naught. And so I got or this was negative, wasn't it? Yeah, I got a minus here and a plus there. So 1 minus 3, 1 minus 3, these cancel out, my phi naughts cancel out, and I'm left with t. So that entire term goes to just t. And so that results in the simplified expression for the inventory of isotope 3 equal to n1 naught times lambda 2. Oh, this lambda 2 here is going to cancel with that lambda 2. That's right. Gamma 1 phi naught multiplied by t. That entire term went to t. And then this one will be 1 over lambda 2 times 1 minus exponential of minus lambda 2t. So these were fairly complicated expressions. We've simplified each of them, but it's important for us to ask how appropriate was that simplification. Were these assumptions valid assumptions to make? And the way that we answer that is to look at the actual values. So for what we had in the problem for example 13.1, we had deuterium and then tritium and then helium-3. And so if we look up numbers for lambda 2 and we compare that to the cross section multiplied by the flux, then this is going to be 3.5 times 10 to the 6th. And if we do the same thing and compare that to the cross section for isotope 2, then we put those numbers in there, and that's going to be 3 times 10 to the 6th, times 10 to the 8th. And we do that for the third one, not lambda 3, but lambda 2. And in this case, we're going to be 3.2 times 10 to the 7th. And if we ask ourselves, well, what were we looking for? We were looking for lambda to be much, much larger than any of the cross sections multiplied by the neutron flux. And that's exactly what we have. We've got everything's more than 3 million times bigger. And so we feel very confident with that one. And now we want to look at the second assumption that we made, which was related to time, the time window. And so we'll compare the arguments of any kind of exponential that had time and sigma and phi in there. So t times, well, we ask ourselves, what was the time? The longest time we were going to consider was 300 years. This is going to be 9.47 times 10 to the 9th seconds. And so if we look at even something as long as 300 years, then we want to look at 1 times phi naught, and that's going to equal 4.8 times 10 to the negative 6th. And we do that again for isotope 2, the cross-section for isotope 2. That's going to be equal to 5.7 times 10 to the negative 8th. And then finally for isotope 3. And we find out that's going to be 5.2 times 10 to the negative 7th. And that's what we wanted, that's what we were hoping to see, is that the product of those three was much, much smaller than 1, and that's what we get. In fact, we get something that's 1 million times smaller than that. And so the conclusion here is that those assumptions that we made are indeed valid. And so we feel very comfortable using the simplified expressions rather than the full-blown equations in this particular problem. And you'll find that most activation applications that one would look at or one would be interested in, then these relationships are pretty consistent in almost every case. And so it's typically we feel very comfortable using those simplified expressions. And what's important to note here is that this one in particular, this one here is related to the activity of isotope number 2. And isotope 2 in general, that's the thing we're after. When we do some activation experiment, we put something in there that's stable and we get an unstable isotope. We want to know what the activity is as a function of time. We want to know how long we need to insert that in there. And you see that as we viewed on that activity plot in MATLAB, we saw that it seemed to approach some asymptotic value, some saturation value. And so that's exactly what we're looking at here. Right? As time gets large, then we're left with this. So that is our saturation inventory. And if we multiply that by lambda 2, which would just cancel this lambda 2 in the denominator, we get the saturation activity. And so that's what we want to look at. And we want to say, well, how long do I need to keep the sample in there before I reach 90% or 80% of the saturation? I know if I keep it in there for a really long time, 300 years, then I'm going to approach this saturation value for activity or inventory. So it's not worth it for me to keep it in there 300 years. If I can get 80% of that in 10 years, then I obviously want to do that, or 60% in a year, or whatever it is. All right, so let's go back to the notes. So we want to take those full expressions for N2. Notice as I mentioned, we didn't zoom in on this in the plots or anything, but the full expression here has two competing exponentials. And so it's going to, at some point, it looked like it was saturated, but if we kept going 400, 500, 1,000, 2,000 years, we're going to start to see that activity start to decay again. And so there is a peak somewhere in there. And again, it's a very, very flat curve, and so we can be really flexible. reaching that peak. But we want to know where that time is that maximizes the activity for isotope number 2. And so we would take this expression, take the derivative of it, set it equal to 0, solve for time. We're just going to, in interest of time here, we're just going to write the expression for that Tmax. This is the time when the derivative of d2, or ddt, of that isotope number 2 equals 0. And this is going to be the following. Tmax is going to be 1 divided by lambda 2 So that's the expression for my Tmax. And why do I care about that? Because that tells me that if I actually were to insert this sample into that reactor for longer than this value, then the activity is going to start to go down. And if I'm looking to keep it in there so that I get as much activity as I can, big bang for the buck, so to speak, then I know that whatever that Tmax is, I don't want to go above it. And so, you're not going to find that by looking at the simplified form of these expressions, but we do get that from this more full-blown expression. And so if we go to example number 3, we want to find, in this tritium activity example that we've been working with on 1 and 2, we want to find the time at which that activity is maximized. And then we want to look at that expression. We can maybe further simplify that based on what order of magnitude between different terms. But first, let's calculate that maximum activity, or the time to the maximum activity. Our expression was that Tmax 1 over lambda 2 minus phi naught multiplied by the natural log of lambda 2 plus gamma 2 over cross-section of isotope 1 and the neutron flux there. And so if I substitute all the values for lambda 2, the cross-section data, the phi given in the problem statement, then I find out this is going to be 8.45 times 10 to the 9th seconds, which is going to be 267.9 years. So a little shy of 300 years. But I can also, as the problem statement suggests, I can take these, and just as I did before, this is going to approximately be equal to lambda 2, as is this here. And so the simplified expression for this maximum time is going to be 1 over lambda 2 times the natural log of lambda 2 over the cross-section and the neutron flux. And if you do this calculation, you get this is exactly the same, 0.9 years. And it's not surprising given the fact that the simplifications we made from here to here, only the simplifications we made there were on the orders of 5 to 6 orders of magnitude difference between these terms that we're adding together. And so, we shouldn't be surprised that happens. And so we want to now know what the resulting expression for time to maximum activity, that's what this is here. And we want to say how long would it take to reach 90% of that. So I don't want to wait 267.9 years to reach maximum activity. I want to see how long I should put the sample in the reactor if I only want to get to 90% of that. And if that number is too large, I keep dialing it down to see what activity could I get in 10 years or 5 years or however long I'm comfortable putting that into the keeping that into the reactor. So for the simplified expression for N2, that's where we're going to find the activity. The activity is going to be the inventory multiplied by the decay constant, which is just going to be equal to lambda 2 times n1 naught times the cross section over lambda 2. Automatically I can see these two are going to cancel each other out. Multiply by 1 times the exponential of minus lambda 2t. So what is my saturated value? My saturated value is this here, right, what's left over. That's going to be A2 sat. Your book calls this A2 infinity. Those two are going to be the same, but this is just equal to n, my initial inventory for isotope 1 times the gamma cross-section times the absorption cross-section of isotope 1 multiplied by that neutron flux. And so I can also just express this as A2 as a function of t equals that saturation value for A2 multiplied by 1 minus the exponential of minus lambda 2t. And that saturation value is the peak. Right? I know that it's going to take 267.9 years to get there, but once I do get there, the activity is going to be equal to this here. N10 multiplied by the cross-section, the absorption cross-section of isotope 1 multiplied by the neutron flux. And so I want to see, well, I want to find the time to reach some fraction of that. Well, the fraction we're looking at is 90%. Let's keep it more general than that for argument's sake and for more completeness here. So what we'll say is we want to find the time, call this TF, to reach some fraction of that saturation value. And again, in our case, we're gonna use 0.90, or 0.9 for that. But so the left-hand side of this just becomes F times A2 sat equals A2 sat 1 minus the exponential of minus lambda 2 times t. In this case, t is going to be that TF, what I'm looking for there. So these two are gone, and I can easily just solve this for TF. And I'll find that TF is just going to be 1 over lambda 2 times the natural log of 1 divided by 1 minus F. So now I just plug in F equals 0.9 because that's what the problem statement is specifying. Then TF is going to equal 40.9 years, which is still a long time compared to maybe what the time constant or the needs are for tritium, for example. But I know that I'm quickly reaching that. In other words, in a sixth of the time that it would take me to reach that full saturation activity, 40 versus 260, in a sixth of the time, I'm all the way up to 90% of the maximum activity that I would ever hope to see in that sample. And so, I can play with this a little bit, but the point that you need to understand from this is that activity is going to build up quickly at the beginning, and then it's going to slowly reach that saturation value. And so there's not as much incentive to keep it in there past 40 years in this example. Right? I can wait another 220 years, and I'm only getting a little bit more activity out of it. Okay, so that's example 3, and that kind of summarizes the activity problem in general. We now want to take a look at what happens after we remove that. So our whole goal was to insert this sample in there to get tritium, for example, and once we take it out, how long do we have before this decays away anyway? And so how long do we have to use it? What happens to it after we remove it from the reactor? So here's the question here: what is the activity of the sample after inserting into the neutron flux for some time? So we keep it in there in case of a few years or 10 years or whatever. That's going to be our capital T. That's how long we keep it in the reactor and is exposed to that neutron flux, and then we take it out, and then we want to know what that activity looks like. So we know that from 0 to that capital T, then it's going to be subject to the neutron flux. It's going to be the same activation equations that we've been using. So this is going to be my sample here. We'll just call this A2 sat 1 minus exponential minus lambda 2t. That is my expression. And so after time equal to capital T, then this simply becomes equal A2 sat 1 minus exponential minus lambda 2 capital T. So that now is the initial activity once I take it out. And then it's going to start to decay after that, because now there's no longer any neutrons bouncing around. I don't have a neutron flux. And so the only sink that I have at that point is the decay, the radioactive decay. And so at that point, A2 of T, now little t, where T is greater than that capital T, then this will be equal to that initial activity. I'll go ahead and put and substitute back in what that saturation activity is, times the cross-section multiplied by the neutron flux times 1 minus exponential of negative lambda 2t. That is my initial activity. After the irradiation. But now I've got to multiply that whole thing by the exponential decay due to the decay. And so this then is just become T minus capital T. And we're going to let this be greater than or equal to 0. And so the difference between that T minus capital T, that represents the time that now it's been outside the reactor, the time since one has extracted that from the reactor, removed it from the reactor. Let's do a quick example of that now. So we want to consider the neutron activation of chlorine-37 to produce chlorine-38. We want to determine the activity normalized by the saturation activity after the sample was placed in the reactor for 2 hours. So this here is going to be our capital T. It's been in there in the reactor for 2 hours. We want to determine the activity. So we want to find out what the activity is after 2 hours. And then we also want to determine the activity, and we're going to normalize that again after 1 hour being removed from the reactor. And so T in this case is going to be 3 hours, so that T minus capital T is equal to 1 hour. 1 hour outside the reactor for part B. So in part A, what we'll do is just model it with the activation equation that we just had. So for T equal to capital T, then we just say that our activation after 2 hours been in the reactor, well, this was a sat here, A2 sat, and we want to normalize this, and so we move it over to the other side. This will just be 1 minus exponential of minus lambda 2 times that T, where T again is going to be 2 hours. And so we find out this case that A2 of T divided by that saturation is just going to be 1 minus exponential of minus lambda 2T. And for our data, this is going to be 0.893. So I insert it in there for 2 hours, and I've got almost 90% of the activity I could ever hope to get. And then it's removed in part B. So after removal, then A2 of t over that same saturation is going to be that initial activity, which was 0.893, multiplied by the exponential of minus lambda 2 t minus t. And this here, t minus t here, is going to be equal to 1 hour. And if I do that math, then I get that A2 of t over A2 sat is going to be equal to 0.292. So it's been inserted for 2 hours. It reaches almost 90% of the maximum activity that it would ever get. And then after just 1 hour of being outside the reactor, it's already dropped down to less than 30% of that maximum activity, of that saturation activity. And so graphically what's happening here as a function of time, within the reactor, this is going to be, here's my saturation value. Within the reactor, it's going to, if I leave it there forever, it's going to approach that asymptotically or in an exponential fashion. But this problem is saying that we remove it at some point here, and then outside of the reactor, it's just going to do some sort of exponential decay. And this actually is going to be a higher rate in this problem. And so this is the time history of what we expect it to do for activity. Okay, let's go back to a few more things with the notes. One more thing with the note, actually. So we'll find the last topic that we'll cover here is related to exploiting the decay in order to determine the age of something. The examples listed in the book are the age of relics, geological samples, that sort of thing. If we have a simple closed system with an unstable parent and a stable daughter, then we know that the inventory of these at any given moment in time has to be equal to the initial inventory of nuclide number 1. This again is assuming the initial inventory of isotope 2 was 0. And we already know how this decays. It decays like the following. And so if we solve that for n1 naught, that'll just be n1 of t multiplied by the exponential of positive lambda 1t. And so we're going to take this and substitute it in here. And so what we get is n1 plus n2 equals n1 times the exponential of lambda 1t. And so we will simply divide that now and divide everything by n1, so we get the exponential of lambda 1t equals 1 plus n2 of t over n1 of t. Take the natural log of both sides, and you find out that that time is going to be equal to the 1 over the decay constant times 1 plus n2 over n1 of t. So at any given moment in time, if I have some spectrometric measurement that I can make, I can estimate the relative population of isotope 2 compared to isotope 1. That's going to be my input here. And if I know the half-life of that radioisotope number 1, then I can calculate how much time has elapsed in order for that ratio here to be achieved. And so we're not going to go through this in detail, but I thought I'd just give the example in the text. Example number 28 in this chapter of the text, radiodating with thorium-232. And so you can walk through this, but you'll see the thing I want to draw your attention to is this here. We want to find some time. In this case, we're looking at the age of this these sources, and you can see that this is very close to the accepted age of the Earth, for example. But we're using the half-life here, and this is just a ratio of what we measure in today's metrics. Okay, so that concludes this lecture. The next lecture we'll start talking about fission and fusion and incorporating that into the framework that we've already talked about at great length. If you think about a uranium-235 nucleus that undergoes fission, then now I have two daughter products, these fission products. That process now became a source for each of those two daughters. And so now I can look at the likelihood of different daughters coming from this fission event and start to account for all the inventory that way. But that'll be next lecture. That concludes this lecture. Thank you.